Hello, I'm Jonas, obviously, and this is my quantum presentation. I'm going to be talking about CP violation, specifically in neutral kaon systems, but also more generally. So let's get started, shall we? First, I'm going to talk about discrete symmetries. So we're going to talk about parity, charge conjugation, and then time reversal. So first up is parity, and that is we are doing a spatial coordinate inversion. So parity on some position state will give us the sign flip of that position state, right? Then this allows us to discuss two different types of vectors. So we either have polar vectors, which change sign under parity, or axial vectors, which don't. So an example of a polar vector is x, or p, position or momentum, which change sign under parity, but then something like angular momentum won't, because it's made up of a cross product between the two. So if we apply parity on x, we get a negative x, and then on p, we get negative p. So in total, the sign is unchanged if we apply parity onto angular momentum. And then important properties here, we have that it's unitary and linear. So unitary means that its inverse is the same as its Hermitian conjugate, meaning that this is true, that the p dagger p is equal to I. Okay, so that's parity. Next up is charge conjugation, which, aside from the name saying charge conjugation, it changes matter for antimatter. So charge conjugation on an electron gives us a positron, charge conjugation on a neutron gives us an antineutron, and then something that is its own antiparticle, like a photon, is an eigenstate of charge conjugation. And we generally choose -1 for C on a photon by convention. So generally these one particle states won't be eigenstates of C. We, for the most part, have to construct some superposition, which we'll see later with kaons, to get a state of charge conjugation. And as I said, the name is a bit of a misnomer. We can act it on neutral particles, such as the neutron, and get an antineutron in return. All right, and third, we have time reversal. Time reversal is a bit different, right? What we do when we act time reversal is we take the conjugate of a state. So we have t on psi, and we get psi star, which is the time reverse state of psi. Now, aside from C and P, T doesn't really have any eigenstates. You can't really construct a state that's an eigenstate of T because we're taking a complex conjugate of it. So that's an important fact, and that makes it kind of hard to measure whether T is a good symmetry or not. But aside from that, time reversal acts on states and operators and also C numbers. So that makes it anti-linear as opposed to C and P being linear. T is anti-linear, meaning that if we have T on some C number A and some state psi, we have to take the conjugate of A and then act it on psi, which is a bit different than C and P. Okay, so there used to be something called the tau theta puzzle, where we had these two particles with these two decays. We had tau plus decayed into 2 pions, a pi plus or a pi zero, and then theta plus decaying into 3 pions, a pi plus, pi minus. These seem like different particles, but they turn out not to be. They have the same mass and the same lifetime, but two separate decays, which is interesting because they also have different parities, right? The parity of a pion's -1, so the parity of this final state is +1. The parity of this final state is -1. So if this is the same particle, that just maximally violates parity, which is a problem, because at the time it seemed like parity was a good symmetry of every interaction. And this was kind of upended when Li and Yang proposed that these were the same particle and parity just isn't conserved. And this became a Nobel Prize for these two. And Chien-Shiung Wu in 1956 performed an experiment on the beta decay of cobalt-60 that kind of proved that this was the case, right? So what we're doing in parity is we're doing a spatial inversion, right? Meaning that if we had some decay and we measured the spatial distribution of the products of the decay and then performed parity, it would do the same thing, meaning that the it's invariant under the spatial inversion, meaning that the particle distribution as they come out doesn't care about the direction specifically, because if it did, and then we applied parity on it, they wouldn't be the same reaction, meaning the parity wouldn't be conserved. So this was kind of the goal of the Wu experiment, which is this decay here. So we have cobalt-60 decaying into an excited state of nickel, which is where these two photons come from, and that's kind of the reason why this experiment was so, or this reaction specifically was so important, is because these photons are emitted from an excited state of nickel through the electromagnetic interaction, which does conserve parity. So we could look at the distribution of these photons as they come out as decay products and compare them to the distribution of these electrons and see if there's any disparity there, because we know that the photons will respect parity, meaning they don't care where they get emitted. So if the electrons do, we can say that the weak interaction, which is what produces this electron and this antineutrino, don't respect parity, which is exactly what this experiment does. In the experiment itself, the electrons preferred a direction opposite to the spin of the cobalt, right? So they're emitted in that direction, meaning since spin doesn't change under parity, because spin is an axial vector as well, the fact that it will emit opposite the sign of, or opposite the direction of spin every time, shows that parity isn't conserved, because as we apply parity, spin doesn't change, all the other spatial coordinates do, so the direction of the electron emission changes sign as well. So this was a huge experiment in showing that parity is not conserved in beta decay, or more specifically the weak interaction. Now, an important aspect of this was the spin, right? So what we're going to look at now is helicity, and this equation up here shows how helicity is defined, right? So we're either going to get +1 or -1 because of the way that this is defined, but we have momentum and spin. So helicity basically tells us if the direction of momentum and direction of spin are aligned in the same way. And notice this is not Lorentz invariant, right? If we have something that's going in a certain momentum with a certain spin, and then we boost into a frame where it's going, where the momentum now switches directions, the helicity won't be the same. So this is not a Lorentz invariant quantity, which is important for most particles. If we have something like a massless particle with spin, like a photon, we can't boost into a frame where we're going faster than it effectively, meaning that we can't change the sign of momentum, and helicity then becomes Lorentz invariant for something that's massless, or something that's near massless, like neutrinos. But anyway, applying parity to this as well is important, because like I said, momentum is a vector, or a polar vector, and spin is an axial vector, meaning that this will change sign under parity. And that's important because of neutrinos. Now, what we do here is we take neutrinos to be nearly massless, such that all neutrinos, all of them, are always left-handed, meaning that h is -1. And all antineutrinos are right-handed, meaning h equals +1. And this is what's been observed. There's never been a right-handed neutrino observed, and there's never been a left-handed antineutrino. Right? So this is a problem for neutrinos and parity, if we want to take parity as a good symmetry, because we only have left-handed neutrinos, and we only have right-handed antineutrinos. So what happens when we act parity on a left-handed neutrino is we get a right-handed neutrino, because the sign of the momentum switches, but the sign of the spin doesn't, right? Same thing here. We take this is an antineutrino with a bar on top here. We take a right-handed antineutrino and put parity on it, and now it's a left-handed antineutrino. These two things on the right don't appear in nature ever. We've never seen these, meaning that neutrinos seem to violate parity. Same thing with charge conjugation. If we do charge conjugation, all we do is flip the antimatter and matter. We don't change the handedness, the momentum, or the spin of the particle, right? So we apply charge conjugation to a left-handed neutrino. We get an anti-left-handed neutrino, which doesn't exist. We apply charge conjugation to an anti-right-handed neutrino. We get a right-handed neutrino, which doesn't exist. But if we combine the two, we get something that does, right? So we apply parity to the left-handed neutrino, we get a right-handed neutrino, doesn't exist. Apply charge conjugation, we get something that does exist, a right-handed antineutrino. So And also, neutrinos are only produced in weak interactions. So this kind of indicates that CP, charge conjugation, and parity together might be a good symmetry for the weak interaction. Okay, we are going to do a quick aside and talk about neutral kaons. Now, will tie back into what we just talked about with quark mixing and the weak interaction, but first let's introduce these. So we have the K0 and the anti-K0 here made up of a down and an anti-strange for the K0 and an anti-down and a strange for the anti-K0. Now these are strangeness eigenstates, and we're going to express them in a different basis in a little bit, but these come from strong processes, so we know how to express them in terms of the strangeness because of their production from strong processes, specifically these s equals 0 strong processes, and I've written these out here. So we send a pi minus beam into a proton target and get this lambda baryon and this K0 meson. The pion doesn't have any strangeness, the proton doesn't have any strangeness. This has a strange quark in it, and this has an anti-strange quark in it, so we preserve strangeness, which is a property of the strong interaction. Same thing with pi plus, we send a pi plus beam, again no strangeness, into a proton target, no strangeness, we get a K plus, which has an anti-strange, and then an anti-K0, which has a strange and a proton, so we preserve strangeness here as well. So how these are produced are from a strong process. That's why we know how to describe them in terms of their quark constituents, their strong eigenstate constituents. Now, we're interested now in their weak, how they interact with the weak vector bosons, specifically the W minus, W plus, and specifically in terms of CP symmetry, because we suspect that the weak interaction is symmetric under C and P together, so we want to construct CP eigenstates of these K0 and anti-K0. Before we do that, we have to know how parity acts on it, and we have to know how charge conjugation acts on it. So kaons are pseudoscalars, and that means that parity on the kaon will return a -1 eigenvalue, right? So same thing for the anti-kaon. Then for charge conjugation, we take this +1 phase convention and we say that charge conjugation on the kaon gives us an anti-kaon. So with that in mind, what we want to do is construct eigenstates of CP together. So to do that, we call them K1 and K2, and we have the difference, and then we have the sum. And because we suspect that the weak interaction preserves CP, when we observe weak decays involving kaons, we suspect that they are these K1s and K0s, because these are CP eigenstates, and I'll show that. That's what this is, or that's what the these two lines are. But first, it's important to understand these have been measured, these have been detected, right? They have this decays differently than this does in the weak process. So these specifically are eigenstates of the weak interaction, or so we think. That is, these CP eigenstates they preserve their CP eigenstates, and we suspect that the weak interaction preserves charge and parity together. So what we're going to do is we're going to call these something else. We're going to call these KL for K2, that's what this is, and KS for K1, that's what this is. And if we act CP on KL, we see that we just break it down into what we know, how we know C and P act on these kaons, and we see that we get minus KL, or a -1 value for CP, -1 eigenvalue for CP, and then for KS we get +1. Now, that's important because, like I said, the weak decays involving kaons have been measured, and we see that we get two different decays. We get Ks into 2 pions with a very, very short lifetime, and then Kl into 3 pions with a much longer lifetime. So we brand them Kl for long-lived and Ks for short-lived. Now, our assumption right now is that these Kls and Ks are exactly the same as these K1s and K2s, and that assumption is based purely in the fact that the weak interaction preserves CP symmetry. So if it doesn't, this Ks and Kl are not the same as K1 and K2, and we're going to talk about that here in a second. But first, we are going to talk about the Cronin and Fitch experiment, which is the experiment using these weak interacting kaons to show that there's CP violation. First, though, charge conjugation on pions. Pi 0 is its own antiparticle. Pi plus and pi minus are C conjugates of each other. And parity is odd for all types of pions, meaning that 2-pion state, I'll go back to the previous slide, here we have this 2-pion state for Ks, and we have the 3-pion state for Kl, meaning that a 2-pion state we get Cp plus 1, and a 3-pion state Cp minus 1. And again, I'll go back to the previous slide, we know that Cp is minus 1 for this Kl, and we see that Cp is conserved in this. If Kl has Cp minus 1, and 3 pions have Cp minus 1, Cp is conserved. Ks has Cp plus 1. The 2 pions has Cp plus 1, meaning that Cp is conserved. Now, that means that Kl can only decay into 3 pions if Cp is preserved, and Ks can only decay into 2 pions if Cp is conserved. So the aim of the Cronin and Fitch experiment is to basically test this, show if that's true. So we produce neutral kaons via strong processes, the reactions I showed a couple slides ago with the pion beams and the proton targets, and then we send that down a 57-foot beam line. Now, even if these kaons were moving at nearly the speed of light, like 0.98 c, these short-lived kaons would only make it a few meters before they all decay. That means that at the very end of this 57-foot beam line, we should only have KLs left. That means we should only see 3 pion decays. No 2 pion decays. All of the KSs have decayed effectively. There should be no 2 pion decays. However, what they saw is that they got 45 2 pion decays out of 22,700 events. That's too many for Cp to be conserved. So this indicates that Cp isn't conserved. And specifically that Kl and K2 aren't exactly equal, and Ks and K1 aren't exactly equal. Now remember, the way that we define these is this K2 and K1, those are the Cp eigenstates. The Ks and the Kl are the physical particles that we're seeing the decays of. So if we saw 45 2 pion decays, that means that Kl isn't just K2, but it's also a very small amount of K1. And the other way, alternatively, Ks isn't just K1, it's a small amount of K2, with this epsilon being a measure of Cp violation. So first, I have the K2 and K1 definitions written up here in terms of K0 and K bar, and then I have written our Kl and Ks in terms of K1 and K2, K1 and K2 that we found just in the slides right now. So we have this small epsilon that dictates basically how much of K1 is in Kl and how much of K2 is in how much they mix, right? So what I'm going to do is I'm going to write our initial assumption sort of just with Kl here, where we have 1 over root 2 p K0 plus q K0 bar, right? So these are just some undetermined expansion coefficients for now that we're going to hold as p and q, and as we know, if Cp is conserved, this p and this q are both 1, meaning that this is a Cp eigenstate. As we know, that's not true, so what we're going to do is we're going to write this p and q in terms of epsilon in order to sort of quantify how much Cp is violated. So what I'm going to do is I'm going to put in K2 and K1 into KL and then compare the two. So here we're going to expand KL0, and this A is just a normalization coefficient, which you can see on the slides. We have A 1 over root 2 K0 plus K bar plus epsilon K0 minus K0 bar, right? Then we can rewrite this as A over root 2, 1 plus epsilon K0, 1 minus epsilon K bar. So then we can just look at this, right, and say that this is P and this is Q. So we can, I'm going to write it as one condition. We can just write Q over P is equal to 1 minus epsilon over 1 plus epsilon, right? So then basically the condition is if Q over P is equal to 1, Cp is good symmetry, right? If it's not equal to 1, we get CP violation, right? And we can see if this epsilon is non-zero, we get CP violation. Yeah, so we do have a measurement. Basically, we can find that this mixing is true, and we do have a measured value for this epsilon, right? We find that epsilon is 2.228 plus or minus 0.011 times 10 to the third. That would be 10 to the minus third, of course. So it's quite a small value, but that is basically a measure of indirect CP violation. That's violation through something called kaon oscillation, or through mixing, right? Yeah, so anytime that there's CP violation through mixing, through this sort of mixing process that I've shown here, we call that indirect CP violation, and is measured by this quantity. And generally it's described by a second order weak process called kaon oscillation. That is, the neutral kaon can become its antiparticle and vice versa. So I'm going to draw that diagram really quick. All right, so we have two contributions at second order here. We have, first I'll just write K0. We have a down and anti-strange. Two vertices here, where we have a W minus into a strange and an anti-down, with this being any sort of upper level quark. That means up, charm, top, anything like that. The highest favored one is the charm quark, but again, application of the 2x2 matrix we showed earlier, that these vertices, we have those matrix elements interacting, right? So let's say this is an up, and this is an up. At this vertex, we have VUD. At this vertex, we have VUS. At this vertex, we have VUD, and at this vertex, we have VUS. So, yeah, so generally I think charm is the most favorable here, but it could be any of the three. So this plus the second one, which is some kaon here, down, strange, we go all the way across, two vertices, all the way across, two vertices, and we exchange here, down, where this becomes a strange. Again, this can be, and this becomes a down bar, K0, where this can be any of the three upper quark generations, and these again are W minuses. So two second order weak processes that describe kaons becoming their own antiparticle. These are weak interactions as well, so we don't see this on a scale of the strong interaction because they're so different in time scale, but these two are sort of what contribute to indirect CP violation. Okay. So now in terms of just decay, or what we're going to call direct CP violation, we're interested in these two decays, right? Because we know that KL and KR both decay into 2 pi. So what we want to do is we want to define these ratios. We have a to 0, 0, which gives pi 0, KL, and pi 0, KS. I call it KR again, KS. And then eta plus minus is equal to pi plus pi minus KL over pi plus pi minus KS. Right, so since these are neutral, right, these can decay either into pi 0, or pi plus pi minus, and then we can define the ratios of the two. These decays should be symmetric if CP is conserved. experimentally we can calculate these things, right? We can say, okay, we can find that this is just the amplitude of, these processes, which we can make experiments for. We get 2.220, that's supposed to be a plus minus 0.011 times 10 to the minus 3. And this is equal to 2.232 plus minus 0.011 times 10 to the minus 3. So they're not the same, right? So we can do this ratio, I should say, and find that this is 0.9950 plus or minus 0.0007, right? Now, clearly this is not 1, but it's pretty close to 1, right? So this sort of shows that CPU violation in the weak interaction is a small effect. It's a relatively small effect, primarily coming from epsilon, right? Indirect CP violation, and what we're going to call epsilon prime as a measure of direct CP violation, where we can see, based on what I wrote earlier for epsilon, that eta 0, 0 is epsilon minus 2 epsilon prime, and eta plus minus is equal to epsilon minus epsilon prime. So we can see that direct CP violation, or I should say, sorry, if we don't have direct CP violation, these ratios are the same, right? And they're just related to that CP violation from mixing. So this is different. And this also has two sort of primary contributors to the diagrams. This is a first order weak process though. So this is specifically k to pi pi. So we have a k0 as a s and a d. Where this is a w minus, this is a u, this is a d, that's an anti-d, and that is a u. So we have a pi plus, pi minus, and then also contributing to this, we have what's called the penguin diagram. Which includes this strong interaction. Sorry, these are anti-quarks. That's a d prime, that's a u, that's a anti-u. Oh wait, no, sorry. That's a d. So we get a pi plus. Sorry, that's a pi plus, that's a pi minus. Okay, so these two are the leading contributing diagrams to direct CP violation. That is sort of asymmetry in the two k to pi pi decays. That if they were the same, we would get a 1 for that ratio, and we don't. So that's two separate CP violations. And again, these are small parameters, right? Like what we saw with parity, that parity is pretty much all the way violated, as much as it could be. The CP is just a very tiny violation. Like it's very close to a symmetry, which is quite interesting. So.